to the Atma Paradigm. We continue part 4 of our series entitled The Universe and Beyond. And our title today is Pre-Temporal Reality. Is there something before the start of time? Can we ask such a question, or is it just a nonsensical paradox? So why are so many cosmologists asking this question? Well, I think it's because of what we explored last week. That we considered what existed at the start of the universe, at what is generally regarded as the beginning of time. And we looked at what happened from then until now in terms of the emergence of specific components of physics. That means all the matter and energy and forces that come with it, and the overall structure of the cosmos, the stars, the planets and galaxies and so on. The conclusion is that the early universe has an inordinate amount of highly specified free parameters that define the values and constants of these components of the universe. And it's these components that then go on to produce the overall structure of the universe. Neil Turek, who is a cosmologist working on the start of the universe, comments that the universe looks extremely ordered and symmetrical and simple. And he and others kind of realize that this is just a just right scenario. Everything seems set up in such a way as to produce a universe that is just right for life to exist and to thrive. The challenge for them has been to explain the seeming presence of such precise fine-tuning, and today we're going to look at some of the main propositions which really try to deal with this topic of cosmogony. What is the origin of the universe? So some of these propositions to explain the start and the presence of fine-tuning will try and keep us firmly within this one universe. But some of them require us to wonder, is there a something outside of the universe, something before the start of time and space as we know it in this universe? So let's remind ourselves of some of the key points that we're going to bring forward into today's session. Here's a quick summary of the history according to the standard model of cosmology. Well, the universe starts with, although it's not really quite sure what it starts with, as we shall see. Commonly, it's called the Big Bang, but as cosmologists have joked, it wasn't big, there was no bang, and there may not even have been it might have been because it wasn't a one-off occurrence, perhaps. But the usual description of this starting point is that it is a state of pure energy, generally called a singularity, a point of infinite density, that means infinite mass within an infinitesimal volume of a point, and also at this incredible, practically infinite temperature. Now, that's the point at point zero. And within the first second, that state of pure energy in this early stage of the universe is referred to as kind of a vacuum, meaning that there's no actual matter in it, but it is certainly not a nothingness vacuum. It is a seething sea of quantum probability. And thanks to quantum fluctuations which exist at this point, pairs of particles, they're a pair because one of them is ordinary matter and one of them is a particle of antimatter. And these pairs pop out of this so-called vacuum. They're called virtual particles. Why? Because at this point they do not exist independently of each other. They're a pair. And pretty well as soon as they appear, they interact and disappear. So they don't really take on a physical existence, hence virtual. But still, they're there. And within this first second of the universe, there is a process of inflation in which the volume of space is expanded by 50 or more orders. And this affects those pairs of virtual particles. The pair, individuals get separated, and without being able to annihilate one another, they each become real physical things with mass and energy. And it is the distribution of the energy and mass of these new real particles that produces what are called galaxy seeds, a tiny imprint of variegated energy on space and time. But thanks to inflation, this little kind of seed, which would have been quantum in size, I suppose, is stretched to cosmological proportions. Then, next thing that happens, almost as soon as it starts, inflation stops. We're still within the first fraction of a second. And the expansion of the universe slows to a pace perfect for the future formation of the universe. Now, with the cooling of that sea of energy stuff, it's now plasma. In this plasma, as it cools, it enables the formation of the first fundamental forces, and then the various subatomic particles are produced, and atoms, later on, we get to a stage where atoms can form. And this point is now 380,000 years into the life of the universe. Photons can move freely, and this generates the emission of the cosmic microwave background radiation, the CMB. Now, by this time, the effect of the gravity seeds can be seen in space as areas having more dense and less dense conglomerations of dark matter. And it is this distribution of dark matter that acts as a template for the accretion, the gathering of whatever ordinary matter is nearby. And because there is now a variance of density of matter across space, gravity can do its thing. It begins to draw ordinary matter towards those points. And over the next 100 million years, gravity affects and pulls the mass together and pressurizes it so that the first stars are formed. And then, a little later, or around 500 million to 1 billion years after the start, galaxies form. Now, in this series, I'm not trying to dispute this history. Rather, my point is to focus on the information content of the process. And here is the summary on information that we looked at last week. The early universe is a chaotic state of extremely high entropy. That means high disorder. This means that it's very low information content, according to the theory. You cannot expect the high entropy starting condition of the universe to be able to specify anything other than arbitrary values for the forces and subatomic particles of physics, meaning that their values could be almost anything. But as we saw in previous talks, if they could be anything, then it is amazing that they are the particular values that they do have, because those values are crucial to the way that the universe forms. So out of this kind of high entropy state, a sea of pure energy, the only aspect that is suggested to determine subsequent order involves those fluctuations of quantum probability states, the quantum fluctuations, if you like. And these are presumed, quantum fluctuations are presumed by physics to be entirely random. So you can see our chart. It's indicating what's happening and giving it a kind of rating in terms of information content. We low, high energy start, and we've now got quantum fluctuations which are random. And the one way to think of how these quantum fluctuations are random out of a sea of possibilities is to think of a kind of lottery machine. Here is, because the overall state of all those 50 balls is probabilistic. The setup of these machines is that there's an equal chance that any of the balls will pop out after one turn. But the actual outcome that one turn will produce is a specific numbered ball, say number 42. That's random. So effectively, the specific outcome for our universe as one turn of this cosmic wheel is a wholly random event, unless you want to give special information status to the quantum probability state. And that's a question we're going to explore later. But if we take it as it stands, quantum fluctuations are random, and the stretching of space in which they happen by inflation is also random. We're not saying that there's no reason for inflation to happen, but the stretching of space by it is presumed to have a uniform effect across all of space. So inflation acts uniformly on space, but the variance that it produces results because the locations of those quantum virtual pairs within that space are entirely random. So the positioning and the strengths of the galaxy seeds that inflation plays a hand in stretching is actually also fully random, entirely random. Hence, the variance of energy and mass densities across all of space is also random. And this means that the clumping of dark matter that is affected by those gravity seeds is also random. This means that the standard model offers no suggestion of a specifying source of information for the spatial arrangement of dark matter. And it is dark matter and its clumping, its form, that is credited as being the template for the structure of all subsequent cosmological forms. Hence, the structural template of the universe, that on which the entire universe is constructed, has very, very low information content. So how is it that it produces what Neil Turek said was a universe that looks extremely ordered, symmetrical and simple? Now, the only other organizing effect that is invoked during this whole history that I mentioned is gravity. The accretion of matter being pulled together by gravity. And as we presented last week, that's a very low information process. We showed these three entropy states. When the little cubes are all just laid out in a loose arrangement, that's high entropy. But if they start to accrete, gather around the large block, as in the middle section, well, that's a reduced entropy. But it is nowhere near the level of structure and low entropy that is the third option on the bottom right, where there is specific stacking. So we explained that we would expect gravity to be able to produce the middle arrangement, but we'd be much more surprised if it produced the partially stacked arrangement. Now, no one can say for certain that it is impossible for a low information process to produce some unexpected and unlikely order. But a random, improbable event should not be our first assumption when considering causality, particularly in scientific or philosophical investigations. So I suggest that science and philosophy should proceed on the assumption that order within a system should be accounted for. And I define sources of information for ordered systems as being responsible for the specific decrease in entropy or disorder of that ordered system in order to manifest its function and purpose. Now, I know that the term purpose might seem worrisome to some physicalists who view that the ultimate nature of the universe is purposeless. However, even a physicalist rendition of the cosmology has to acknowledge the function that certain precise parameters of values and constants contribute to producing the overall activity and function of the cosmos as we find it. So we do see that there is function in there, and that's good enough for our definition. I also suggest we should clarify the nature and level of precision that information needs to have in order to order a system effectively. And a source of information should have three requirements. And it must be specifying, it must have sufficient information, and it must be particular. Now, I want to go through that just to kind of show how we should be thinking of a source of information. And we're going to use the children's Lego bricks. Here you see them, a group of them. They come in all these sort of sizes, shapes and colours that you see on the bottom left, but they can be combined into all sorts of very complex constructions. For instance, all those renditions of the famous buildings shown in that picture are created out of Lego bricks. So these constructions are organised structures in a low entropy state compared to their original group of components which scattered on the floor. So you have to ask, what was their source of information? Was the information for these structures entirely present within the building blocks themselves? Now, We can use our formula to look at that. We can question if these building blocks possess all three of those required attributes. Well, in this analogy, you could say the size and shape of each of the building blocks is a type of free parameter. They are what they are, and things will have to be built on them exploiting those characteristics. So, do these blocks contain specifying information? To a small degree, yes. Because their dimensions and the way the studs fit into what are called the anti-studs at the bottom of the bricks, and the way they lock together in specific ways, that is in some way a small amount of specifying information. It specifies how bricks will relate one to another. But such specifying information is very limited. It's a bit like the accretion of matter just kind of gathering around the large block by gravity. These Lego pieces have no preference in which way they connect, other than the rather low information rule of the studs fitting into the anti-studs at the base of the next one. So low specifying content. Thirdly, is there any particular specifying information within these components to account for these buildings being the only or most likely outcome of the ways in which those bricks can interact? So why are we getting a particular outcome from these bricks rather than something else? That's the question that have to be asked. And is that information present within the bricks? And we'd have to say, no, it's not. The information of the bricks can't specify the particularity of the whole structure. It can't even specify the particularity of a small element of that whole structure needed for it to manifest. So we would say that the information content of the bricks on their own does not fulfill our three requirements. The bricks are seen as the material components that these buildings will be made of. But information-wise, the bricks themselves do not contain the required information that is sufficiently specific and particular in order to account for the structures that are produced. Something else must be involved. Now, bearing all these issues in mind, there does seem to be a major disparity in the standard model view of cosmology when it comes to information. As we've said before, a lot of attention on calculations of matter and energy, not so much when it comes to information. So there's disparity between the information content when you look at the fine-tuned properties of the components of matter compared to the low information states that are supposed to be there at the start of the universe. And there's also disparity between the overall organized structure of the universe and the random processes that are said to produce that structure. So in effect, and I don't think this is an oversimplification of the issue, the standard model of cosmology is a narrative of chaos producing order. Now, how do cosmologists cope with this information and entropy disparity? Now, to a degree, this problem is recognized, and many scientists have responded in various ways. And we're going to look at a number of those propositions today. Some try to invoke the powers of chance and possibilities, a kind of stochastic approach, that if something is even remotely possible, well, it might happen. Now, here's one philosophical argument applied by them to explain what seems a highly unlikely scenario and how a highly unlikely scenario can emerge. And it uses a phrase that they've created for this idea called non-equilibrium fluctuation. This is different to the quantum fluctuation. This is a non-equilibrium fluctuation. Now, the proposition is that the universe acquires low entropy for a while. And it's an interesting attempt to address the problem of order arising from a non-ordered state, whilst relying entirely on chance starting conditions and random low information processes. So, brave effort. And we can explain it, the thinking behind this best, by using a kind of standard example given often for the inexorable direction of entropy. And that is a glass of coffee. Now, it's a specific type of glass of coffee. Here it is, with the coffee on the bottom and with cream poured very carefully on top so that it hasn't mixed with the coffee. Now, this is the principle of making Irish coffee, although it has an extra ingredient. And Irish coffee, this setup is possible if you get the temperature of the coffee and the glass high enough. So this configuration of coffee and cream is a state of low entropy. It is carefully constructed and it is not stable. Let the glass stand for a while and the milk and the coffee start to mingle as you have in the middle one and ultimately merge in the one on the right. This is, as I said, the inexorable effect and direction of entropy. It moves from a state of low entropy to a state of high entropy, from order to disorder. And having done this, it seems impossible to really turn the clock back. Can we actually conceive of the opposite flow of entropy, when the coffee and the cream might start off mixed and separate out on their own under natural conditions so that they become the unmixed low entropy state seen on the right? Now that's exactly what is proposed as happening according to the standard model for these people who are proposing non-equilibrium fluctuation. They recognize that's a challenge, but here's what they say, that yes, the universe may start in a high entropy chaotic state of disorder, like our mixed coffee on the left. And yes, it looks like it is acquiring order over time, moving towards this structured state that we have at the moment, structure and low entropy. And I know that seems unlikely, but what you have to appreciate is that the long-term tendency towards disorder does not remove the possibility, however remote that might seem, that in the process there might be a period or a moment of decreased entropy. That within a state of disorder and a process of increasing disorder, there could be a blip of order, which just happens. It would be like the coffee and the cream constituents, although they are kind of going in this direction from mixing together, they decide, no, for a moment we're just going to separate out. A complete chance event. And because it's not a stable state, it lasts just for a moment. And then the cream and the coffee start to mix back again and the situation returns to high entropy. So you could have this picture here, a start of mixture and now of separation and a future of mixed. And they say in that way entropy has not been violated because it has only separated for a moment. So an unexpected random fluctuation against the normal flow of entropy, producing order just for a brief period. I think these pictures are the wrong way around. I apologize for that. I'm going to move on to these things can happen. That what they're suggesting is like this. If you put it in terms of the universe, that we should see our existence in a structured universe as perhaps a blip on the relentless flow towards increasing entropy and the inevitable complete disorder and disintegration of the cosmos. So you might have this picture here, where you start with low information, high entropy, and you produce something which is structured in the middle, low entropy, and then it eventually ends in, that's the universe as we have now, low entropy, high information, but it's just a blip on the path to absolute annihilation. So you don't have to worry about it being a contravention of entropy. Now, cynics might suggest that this is just a fancy way of invoking chance to explain the formation of the structure of the universe. And it hardly seems better than asking us to believe in something rather fanciful. Why? On the basis that, well, if anything is possible, maybe it is possible. Maybe it did happen like that. Now, can someone say with 100% certainty that complex or ordered structures cannot arise by chance? No, we can't. But can someone claim that significant complexity assuredly did arise by chance? Nope. Can they say that it is unlikely but possible? They can stretch it like that. But to those who value logic and reason, it seems absurd that such a postulation reliant on low information states and processes be included within what is a given academic status of a standard model. No problem wanting to believe in these sort of situations of what chance can do for you, the possibilities that might be there. But to use that within the explanation of a standard model of physics and cosmology seems incongruous. So what we propose is that we apply our information test, and that any source of structure and order fulfills the requirements. So information test that any source of information that is going to give structure and order fulfills the requirements of being sufficient, particular, specifying information. Now, here's a different approach by physicists to explain fine-tuning and cosmic structure. And this is to claim, and it kind of borrows on the same sort of stochastic arrangement, that the potential is present in the quantum probability of that vacuum that we talked about emerging at the time of Big Bang. That, and in earlier talks, we had a way of presenting that type of quantum probability state of a system in pictorial form. So here it is. This is kind of a waveform, a quantum waveform within the green brackets. That's our quantum state. And that state has potential. And it's not a manifest situation yet, but there is the opportunity for our quantum state to manifest, in this case, either with the property of being blue or of being red. And the range of probabilities for each property is shown by how much of the wave function is attributed to each possibility. So in this case, we've kind of split it half-half. So 50-50 chance of being red, 50-50 chance of being blue. Now, we perform a measurement to see the color property. And the object obliges by manifesting a specific state, which in this case is the property of being red. That's fine. But the quantum physicists running the mathematics wonder, well, what happened to the rest of the potential of the quantum state? What about the other possibility that existed for the particle to manifest being blue? And one way of trying to deal with that is what's called the many worlds interpretation of quantum physics. And that says that, well, actually, both are produced. The possibility was for both red and blue, and when you did the measurement, both red and blue did get produced. However, we happen to live in the world that has the red one. That's the one we get to see. And there is another universe that is split off from ours, which has the blue one. Now, if this idea were valid, then the universe would be kind of splitting off, or as Hugh Everett, who was the founder of the idea, preferred, that the universe is unraveling from future versions of itself at every moment. So within microseconds, there would be unlimited present versions of the universes existing, and more being created as the quantum future of every particle in the universe at every moment starts to be worked out. So in this way, reality would be an ever unfolding set of infinite parallel worlds, but we are only conscious of one of them. Now, it's an idea that does have many adherents. Amongst the physics world, Sean Carroll, Max Tegmark, Brian Greene, all like this idea. But many others challenge it and consider it a dead-end notion. Because if you're saying that everything that can happen does happen, then you really explain very little about the world and causality. And if the explanation of our own reality is based on postulating the actuality of many parallel worlds that we can perceive, you've actually contravened one of the kind of accepted objectives or principles of science. And that is that it's supposed to explain the world as we experience it. Then you could say, if the splitting or unraveling of the universe entails each one of us also being present in each of those worlds, then the philosophers wonder, well, what does that mean for selfhood? Am I the conscious person in each of those worlds? Or am I the aggregate of all those selves? If so, that means that nothing I do or any choice I make matters. Because if everything is going to get played out anyway, then all the options for every one of my choices are real for me. I will experience them all. So even if I try to enhance the probability, say, of becoming rich by working hard, I will also have experience the other possibilities in which I am poor and lose it all. This is the kind of ultimate zero-sum game. And the other questions would be, well, if the universes, are they producing clones of me at every divergence? So that biologically and physically identical, but with a different conscious self in each clone. And then where does that consciousness come from? So in either case, and then you've got to say, well, which was the consciousness that, anyway, you get into a lot of difficulty addressing this issue of selfhood. And basically, it's ridiculous to have such a theory when you don't have a coherent idea of what the source of consciousness actually is. And because it can't explain consciousness or understand the nature of consciousness, the many worlds interpretation doesn't stand. We've been asked to believe in a picture of reality that can never match or explain what we experience. Now, it's important to remember that this proposition is based on trying to satisfy the mathematical potential of the wave function, and in trying to remove some issues plaguing what is called the Copenhagen interpretation of the collapse of the wave function. Now, it's not part of of what I'm going to explain today, but I would refer to some of you who have a mathematical interest to look into the mathematical argument based on what are called protective measurements, because protective measurements removes the need to suppose that all options, like the red and the blue, have to manifest in different universes. It shows that one universe can accommodate the fact that there is a single outcome from all the many possibilities that exist as potential within the quantum state. Now, perhaps the problems that the many worlds interpretation tries to address come from a presumption that there is no extra factor that might allow the quantum state to manifest a single specific outcome, just as we experience it. And that is something that we want to explore and have talked about a little bit in the past, but will come up a bit more next week. But the many worlds idea still remains seductive to physicists. And some suggest that an aspect of the potential that must exist within the quantum state may apply to the early universe. Let's have a look at that. In this case, the probabilities of the wave function represent, that's the wave we see in the diagram there, represents every possible set of values that could exist for the forces and particles that are going to manifest in due course. So in all the grey areas, the sets of values are not suitable to producing a viable universe. Viable meaning that the outcome, a viable universe would be an outcome that will be a cosmic structure that is suitable for sustaining life. But only one possibility out of all the different sets of values that could be thrown out by the quantum state is shown by the red line just off to the side there. And that red line is the only one that will produce a batch of fine-tuned values and properties that can produce a viable universe. Now, the odds against that possibility are, so to speak, astronomical. But that doesn't matter, because if you're applying the kind of many world scenario that all possibilities occur, well, all the possibilities, the grey, all happen, and also the red one happens. So the one possibility that you need, the red one, produces a viable universe. And it's got the fine-tuned values. All the grey ones also pop into existence, but perhaps they disappear almost immediately or go cold or form nothing useful. We don't know because we have no way of ever interacting with them. So we're just fortunate that to be in the single quantum outcome, which is the perfectly tuned red universe. And of course, one would say, if we weren't in this viable red universe, we wouldn't be marveling at our incredible good fortune. So it really isn't a miracle of chance after all. It's just the way it is for us. However, the spectre of many worlds still comes to haunt this proposition. Because once you accept that the original quantum state can produce unlimited versions of the universe, what happens to the quantum states thereafter? Does the universe keep splitting just as the many worlds interpretation suggests? Are we producing black holes everywhere? Are we producing many selves in this? But one way around this many world situation is to suggest that no, maybe it is possible for there to be one outcome thanks to consciousness. But the way that it is used by many, I think now, I think it's quite a popular idea, is to invoke what is called the anthropic universe. Now, this idea is developed from the recognition that the universe happens to be just right for life. And when we say anthropic, although anthro kind of refers to humans, in this case we kind of mean all life on Earth, plus whatever other life may be out there in distant places. So there are various forms of the anthropic principle. The weak version basically says, well, the universe got it right, and that's just the way it is. We're fortunate to experience it. So in this version, the universe is not interested in our existence and takes no note of it. It just happens that the conditions of physics, etc., have turned out right for life to form, at least on this planet. But there was no plan, it was just fortuitous, and our good fortune of coming into existence means we get to appreciate that good fortune. That's the weak version, and it doesn't really say very much more than what we might have heard earlier. However, there's a strong version, and it suggests that the universe must have the correct properties to ensure circumstances for life to thrive. That's saying that it is an essential aspect of this universe at its beginning and its processes to produce the right conditions for life. It has to be like that. The universe is intended to produce the accommodation of life. Now that raises kind of interesting metaphysical and philosophical questions. Well, how does the universe know what it's supposed to do? How does it ensure going about fulfilling that brief and purpose? And this is addressed by another, a more particular interpretation of the anthropic principle. And that brings in the role of each life form as an observer. An observer meaning in terms of how it's regarded within quantum physics. So it's linked to a particular interpretation of quantum physics, that conscious observers are necessary to bring the universe to life. And this idea is drawn from interpretations of by scientists like Eugene Wigner, John Wheeler, and David Bohm. And the idea is that the later presence of living observers like ourselves produces a bias for particular collapses of the quantum wave function at the start of the universe. And so what we are wanting now, or the fact of our existence now, is feeding back and affecting the collapse of the wave function at the start of the universe so that it favours a universe forming to contain life. So in effect it will kind of look like this. That out of those other options, the grey ones, we actually kind of think, discard them now. Only the red option emerges from the quantum possibilities. Why? Because this is the one option that will produce observers. And it is the presence of those observers, here you see there, you can just about see them with their green smiley faces. It is these observers and the presence of their consciousness that is feeding back and influencing the collapse of that universal wave function to favour only the red outcome that will produce those observers. Now, I have to say this idea is not entertained by all cosmologists, but many physicists are willing to consider it. And this willingness to consider what seems quite an outlandish notion corroborates the importance of several points we've tried to make in these talks. That the information content of the universe must be addressed. That the physics of the standard model has so far failed to explain that information content without invoking the role of consciousness of the observer. And that the aggregated consciousness, and this aggregated consciousness can influence the wave function of the universe without any physical restrictions of time and space. They're willing to consider that that is a possibility. Now, the anthropic universe, as we normally as we've tried to describe it, has its critics. For instance, and one of the issues that people have with it, it seems to rely on what is called reverse causality, that things we do now or want or desire now influence states of physics billions of years ago. But its proponents suggest that perhaps conscious intention is not bound to follow the entropic, not the anthropic, the entropic direction of time, that, order to disorder direction of time. So perhaps the past, present and future are all somehow connected. Now this is very intriguing. But the difficulty for the proponents of the anthropic universe, as we've explained, is that they cannot really give an account for the nature of consciousness, nor can they explain its relationship and interaction with time, space and matter, and how conscious intention can have this agency. But we'll see in due course that we can offer a little help on those questions. But the point is that either way the physicists look at it, the quantum vacuum is full of rich information. So either we have the situation A, where the quantum vacuum possesses all possible states for the unlimited number of universes, out of which only one of them, our red option, is just right, and that's what happens. Or B, it contains the specific set of values that will specify a fine-tuned universe, meaning that it was the only one ever intended to be produced. The nice Goldilocks red option. And as Amanda Gefter, who wrote the book Trespassing on Einstein Law comment, she concluded, somehow, when you look at this situation, you have to think that the laws of physics have been encoded into the fabric of our universe before it existed. Now, it's worth noting that there's always been a strong bias towards finding the answer to everything and how the universe came to be as something ultimately simple. As one scientist joked, a formula you could put on a t-shirt. But complexity from simplicity is not straightforward. What we will see is that supposed simple things contain complex information that itself requires explanation. And that's what we are seeing in these early states of the universe. The Holy Grail has been to find a simple source of complex information. And that was the hope for the singularity. It sounded as simple as you could possibly get. But can this rich information that we need at the starting point be attributed to the singularity itself? Or, as was suggested, does this source of information seem to pre-exist Big Bang? Now that's an almost unthinkable question that many cosmologists are willing to consider. And one reason why they're willing to look at it now is because that the supposed starting point, the singularity itself, is in question. Because when you extrapolate back to Big Bang, the idea is, from a universe that we have now with all the matter, and you're squeezing it, if you kind of go back in the opposite direction of time, you're squeezing it into smaller and smaller volume, and the mass is therefore everything's becoming more dense, and ultimately you reach this point of infinite density and temperature. Now, certainly that seems as simple as you can get. It's just massive energy squeezed into an infinitesimal volume. It's just energy. It's nothing else. There's no forces of nature, no particles. It's just energy. So it's almost a perfect candidate for a simple explanation for our universe. So great if there was a little formula for it. But unfortunately, the singularity turns out not to be as simple or even as possible as it once seemed. The idea that the starting state is a singularity of the universe, that's been debated. And the one question that often comes up is the origins. Where did its energy come from? What was the source of all the stuff of the singularity? That seems to require us to consider there is some form of reality from which the singularity of our universe derived its energy. And there are attempts to get around that inference, but the maths don't look right for a singularity. So this is the other aspect that has challenged the singularity. It's a little tricky, but let me see if I can take you through it. Here's the issue. First of all, we consider the Big Bang kind of standard idea. So at the Big Bang, you've kind of got these tiny this is a tiny, incredible, we can't even imagine the size. The tiny distances, the high density and the high energy state of this early universe would have these incredible, wild quantum fluctuations. They'd be too intense, too wild, and these would produce significant non-uniformities in the distribution of matter. Now, I'm not sure if this drawing is as clear as it can be, but if you have a little look at from the Big Bang, you see it expands to the little kind of shape, star-shaped in the middle, and then again further into the bigger one. And it's got all those kind of lines and squiggles on it. That's showing the warping of space-time. So the idea is that the variation of the mass of matter is what allows gravity to do its things. Gravity has no effect when the density of matter in space is the same in all directions, because everything is pulling on each other to the same degree, so nothing moves. So you can think of it like a tug-of-war team. If the same number of people on each side and they've each got the same strength, the rope remains steady, no one's moving anywhere. But if the two sides have different strengths, then one can pull the other towards it. It's the same with matter. If there is variation in the distribution of matter, then gravity will accentuate that and will make matter clump together, and clumping together of matter warps space-time. And it is this warping of space-time that would be preserved as space expanded and may even become accentuated. So this is what makes the formation of the universe an issue, because if the universe starts with a singularity and there are big differences in those quantum fluctuations, they're just so wild, then the distribution of matter from the very beginning would be too diverse, too non-uniform, and space-time as it began to expand would be warped, so that instead of orderly grids of lines, it's a mess of squiggles. And that represents a cosmos of chaos out there. So inflation would make the situation even worse. So unless there is already uniformity at the starting point of the universe. So we need a starting point that, as shown here, we kind of got our magnifying glass looking at what's there at that beginning part. And we see that in the middle of this second option, we have a regular square grid of space-time at the start. And then after inflation, it still is square. And then over time, the tiny variations of the galaxy seeds start to be affected by gravity, and it produces a kind of variance of distribution of matter. And okay, there's a little bit of movement in the grid, but it's just right for stars to form and then galaxies and so on. So the problem is that this need for uniformity of the distribution of matter at the start doesn't match the calculations for the quantum activity that would be there as you get close to a singularity, which is why the idea of Big Bang singularity as the start is questioned. There needs to be an explanation for a uniform state of energy at the earliest point of the universe, without it ever having been reduced to a singularity. So for many, the singularity is a dead issue. But then what would be a uniform state at that point? if we can't get back to a single point because the quantum fluctuations would be too great at that kind of tiny volume, what must happen? Well, this is the idea of the big bounce, and there's various versions of it. But here's the basic idea, that a previously existing universe with the right uniformity finally collapses in size down, down, down towards a singularity as it ends its life. So coming in from the left, you see it's contracting there. But just before it gets to the point of a singularity, the contraction is reversed, and this tiny kind of thing of matter, of uniform matter, now expands out into the uniform, just right universe that we live in. So this narrative not only tries to explain why the universe is the way it is, how you can have uniformity at the beginning, but it also gives an idea of what might have been there before the start of our universe. And it's suggesting it was a previous universe. So the difficulty with that idea, of course, is that, all right, so you've got a previous universe, and what was before that? Well, it must have been another one. And so it's an infinite regressive universes expanding and collapsing, and that's your only way of explaining the uniformity, but without ever actually getting to grips with the information content. So here is your universe collapsing in on itself, bing, and then back out again, slightly different, and then goes back in again and out again. So something like this, an infinite regress that never reveals the original source of the information or how it got started. Now, there's another theory I'm just going to kind of make reference to, and that is Roger Penrose's idea of what's called conformal cyclic cosmology, CCC. So Penrose is championing this idea because he wants to rival inflation. And he suggests that the universe became uniform before the Big Bang, rather than after it, as inflation suggests. Now, he's not actually proposing that this universe arises from a previous universe. His idea is that this one universe goes through many eons, existing for a time, and then all the matter, gets sucked down into a massive black hole. Over time, the matter actually disappears, meaning that we're back to a pure uniform energy state again. And from this, the universe is reborn, infinitely small and ultra smooth, going through the standard expansion and clumping of matter. So again, no singularity, and you've got the uniformity that you need. But Penrose's theory doesn't address the what's before the universe question, or how this whole process gets started. And when Penrose is asked, well, where's the end of your infinite regress, of the eons of this universe? He says, well, that's a question for philosophy. Seems a bit like kicking the can down the street a little bit. But another way to deal with the information problem is to postulate what's called the multiverse. And this does take us outside of our own universe. Now, the current overall approach to address all the conundrums we've talked about is that our universe is just a small patch of space-time in an infinite volume of space-time patches. And it is this infinite expanse of reality, which isn't really space as we know it within a universe, but in this infinite expanse of reality, universes like ours are infinitely and repeatedly generated. And every conceivable configuration of mass energy permitted by the laws of physics is produced, so that everything that can happen will happen lots of times. So in effect, this is the ultimate monkey cage. The idea that if you need something utterly improbable to happen, you just invoke infinity and eternity to your rescue. And voila, what seemed impossible becomes statistically certain. Now, the theory says that there's no connection or observation is possible between these universes, so we're not going to be able to provide empiric evidence for this. And when asked, well, what is the support for this idea of the multiverse? Well, the answer is, it's the fact of the fine-tuning of this universe. But wait a minute, isn't that what we were trying to explain? How can you use the fact of fine-tuning as the only thing to corroborate your theory to explain the cause behind fine-tuning. It's like the example where the theory of macroevolution is claimed to be justified by the fact that there are different species. So when all said and done, cosmology boils down to this: accept that information, structure and fine-tuning are produced by a reality that needs to try and get it right unlimited times. Now that requires a major element of faith on our part. And now we have a picture of reality that is far, far grander than our puny single universe. That's the one thing that's come out of this. So it sounds like we have something very substantial as pre-temporal reality if we are to go with the multiverse, or if we're to go with any of the other theories. Something beyond this universe has to be invoked. So there is something very substantial as pre-temporal reality. Oh, no, 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 says the physicist. It's actually nothing. And here's the argument for nothing. That they say matter is a positive type of energy and gravity is a negative type of energy. Positive, meaning that particles tend to may want to push each other apart, where gravity tries to pull things together. So when you add them up together, the sum is 0. And that's what you got. There's our sum. Matter and gravity equals 0. And we all know that 0 is nothing. Therefore, from nothing, we have a manifest universe with matter and gravity. And Alan Guth, who we mentioned, I think, last week, he's a physicist, claims that the universe, therefore, may be the ultimate free lunch. Here's a sign from a restaurant. Advertising, free lunch tomorrow. And just as tomorrow never arrives, the saying goes that there's no such thing as a free lunch. But Alan Guth tries to justify the idea of a free lunch, and he suggests, well, maybe a better way of saying it is that something is actually nothing. No, Alan, that's really not much better. You really need to clarify what you mean by nothing and what you mean by something. How are you using these words? But it seems that nothing in physicists' terminology means a state where the physical energy can be balanced at 0. But that balanced 0 state of energy exists within something. Something with the potential to emerge, that it can produce from it unbalanced energy. So that something has the balanced energy, but from it can emerge unbalanced energy, i.e. energy in a differentiated state, such as matter and gravity. So really we have something producing this manifest universe. It may not have physical properties manifest in the way we like to work with them, but it must be real enough to possess the potential to manifest the diversity of physical stuff like matter and gravity. So perhaps we might define this as a non-physical reality capable of giving rise to physical energy. Now, at this point, cosmology is starting to sound rather metaphysical. So even though the free lunch idea doesn't require a source of matter to explain matter, it does need some kind of something. Because as the song goes, nothing ain't worth nothing, but it's free. Cosmology requires there to be a state of reality outside the universe, something outside of time and space that has the potential to give rise to diverse energies which help to manifest cosmic, i.e. within the universe, space and energy. Now, this principle seems to resonate with some of the philosophical principles that we've been identifying along our series. One is a principle of logic that's used in Sankhya analysis, and it's called Satkaryavad. And that is that the potential for a product is contained within its material cause. Now, the example that we've used previously on this is like a lump of clay, which has the potential to manifest a pot. The pot can be produced using only that mixture of clay and water. So we say the clay mixture is the material cause. Now, the same principle is at work within quantum physics, that the outcome is one possibility within the potential of the quantum wave function. And this logic of Satkaryavad also proposes that if something is the cause of something else, then both the cause and its product must be real. Only a real thing can provide the potential for a real thing to be produced from it. So the clay is real, and therefore the pot that is produced from it is also real. Hence we'd suggest that physicists should work on the principle that for this universe to be real, and we hope they think it is, there's something that has the potential, or is the potential material cause for this universe must also be real. It may not be the same physical stuff that they like working with, but it is a form of stuff that can give rise to the full range of material stuff that this universe contains. And in this way, we kind of go bring in another idea that we discussed way back in part 2, which in Sanskrit was called Bheda Bheda, the oneness and difference. And we've seen this principle in many of these concepts of cosmology we've talked about, matter and gravity, equivalent in energy quantity, but simultaneously different in energy quality. And other examples are the quantum states, wave and particle, energy and mass, gravity, space-time. Bheda Bheda, oneness and difference, is a key feature of any description of reality. For cosmology, metaphysics, it doesn't matter. Bheda Bheda is required. So here's a working definition of Bheda Bheda that maybe physicists can use. It is the principle that all facets of reality exist in a connective relationship arising from the simultaneous commonality and distinction of their properties and of their substance and properties. Now, that even though each aspect of physics may be distinct, it enjoys a connective relationship and the ability to interact with the other facets of physical reality thanks to shared aspects of properties and, of course, the fact that they're united by the underlying nature of each of those aspects. And perhaps here is where we find some philosophical agreement with many, though not necessarily all cosmologists, that the fact of the energy that exists at the start of the universe and the fact that there seems to be information embedded into the starting conditions seems to suggest that there must be a something beyond the universe, what I'm going to call an extra universal something, an extra universal source that holds in potential form all the matter that exists within the manifest universes. And I note that I use extra here in its kind of Latin sense as outside of or beyond, not as more of. Okay, so it's outside of beyond. So extra universal refers to a reality outside of the time, space and matter that make up this universe. So the material requirements for our universe can be said to be present in potential state within this extra universal something form of reality. And there are clearly parallels with where we've reached in the metaphysics of cosmology, of both the Western variety and also of the Vedic tradition that I've often talked about. But we do need to remind ourselves that both traditions model the nature of matter very differently. So we shouldn't conflate terms or suggest that particular concepts are equivalent. Today we're trying to explore the issues by applying logical inference on the considerations of modern cosmology. And what we kind of reach is that there is an extra universal source of the energy ingredients for our universe, and that can be accepted as a reasonable hypothesis. David Bohm suggested that we shouldn't really regard this thing that is beyond this kind of vacuum. Rather, we should see it as a plenum. Plenum meaning that it is full, rather than vacuum, which we tend to think of as empty. We talked about the vacuum not being empty, so better to call it a plenum. So really we should not be representing here a kind of patch, a little patch of somethingness, but rather as the expanse of somethingness that everything else is contained within, a realm of potentiality out of which our universe has emerged. It's kind of, I suppose, our bias that we kind of think that space is dark and then everything outside the universe will also kind of be like that. But we've identified the two things that this source of potentiality, this extra universal reality, needs to have to provide our universe with what it needs. And those two things are material, matter in potential state, and information. sufficient specifying information that results in the only or most likely outcome of our universe to appear as it is, perfectly tuned and formed to accommodate life. So these extra universal sources of material information are required to explain how the universe becomes activated, how it produces its component, its laws, its forces and its matter particles, and how it then utilizes those components to manifest order, structure and function. Now, can we go further? Can we offer some explanation of the information content in this extra universal reality? Now, you've heard me say many times that the Atma Paradigm holds as a principle that perhaps the only viable source of specifying information that we can actually identify is consciousness. We know consciousness exists within the universe. It is a real phenomenon. We have built our Atma Paradigm framework on the analysis that consciousness is a fundamental component of reality. And we have strong reason to believe that consciousness is non-temporal, is a non-temporal phenomenon of reality. But there's still questions to be addressed. How consciousness as we know it in our lives relates to the state of consciousness of what we're calling extra-universal reality. What is the nature of consciousness in that context? And what role might it play in determining the content of information of the reality of our universe? Is it possible that each one of us contributes to the unfolding of the universe that we now inhabit? Is cosmic reality the way it is to a degree because of our hopes, desires, and our intentions? In short, do we help to define the universe we later come to inhabit? This will be our topic for next week. So I invite you, join us again for part 5 of this section, the metaphysics of consciousness and our universe. It'll be on the same time on Thursday, 26th of December, the 26th of November at 6 p.m. UK time. And as always, we invite you to send in questions to info@s-pi.org. Thank you very much. Hare Krishna.